In 1986, a single spacecraft flew past Uranus, gathered a few hours of close-up data, and then kept going. No mission has been back since. For nearly 4 decades, almost everything we knew about this planet came from that one brief flyby. But Uranus has not been forgotten by science. Ground-based telescopes, the Hubble Space Telescope, and now the James Webb Space Telescope have kept watching it from a distance, and what they have found has quietly rewritten parts of what we thought we knew. At the same time, scientists are now seriously planning a return mission, and the next good launch window is approaching. So before that happens, it is worth taking a fresh look at this strange, sideways planet. Uranus is the 7th planet from the Sun, orbiting at about 2.9 billion kilometers, roughly 19 times farther from the Sun than Earth. One full orbit, one Uranian year, takes about 84 Earth years. A single day on Uranus, meanwhile, is only about 17 hours long. The most famous thing about Uranus is its tilt. Every planet has an axis it spins around, and most of them are roughly upright relative to their orbit. Uranus is tilted about 98 degrees. In practical terms, the planet is lying on its side, rolling around the Sun like a ball instead of spinning like a top. Neptune, the next most tilted planet, leans only about 28 degrees, nowhere close. This extreme tilt creates the most extreme seasons of any planet in the solar system. Each pole spends roughly 42 years in continuous daylight, followed by roughly 42 years of continuous darkness. Imagine being born at the start of a Uranian winter and never seeing the sun rise at your location for your entire childhood. Until 1986, that was close to the limit of our knowledge. We knew Uranus was an ice giant, we knew of 5 moons, and we knew of a faint ring system. Then Voyager 2 arrived. The flyby lasted only hours, but it transformed our understanding. Voyager 2 measured the atmosphere at around -224 degrees Celsius, making Uranus the coldest planet in the solar system, even colder than Neptune, which is much farther from the Sun. That was unexpected, and it remains one of the biggest open questions about the planet. Voyager 2 also detected something stranger. A magnetic field tilted nearly 60 degrees from the planet's rotation axis and offset from the planet's center. No other planet has a magnetic field arranged quite like it. On top of that, the spacecraft discovered 11 new moons and 2 additional rings, bringing the known moon count to 16 and revealing a more complex ring system than anyone expected. In the images Voyager 2 sent back, Uranus looked almost featureless, a smooth, pale blue-green ball with barely a cloud in sight. That calm appearance turned out to be misleading. Uranus's blue-green color comes from methane in its upper atmosphere. The planet is mostly hydrogen and helium, like the other gas and ice giants, but roughly 2% of its atmosphere is methane. Methane absorbs red light very effectively, so the light reflected back into space is enriched in blue and green wavelengths. That is the color we see. Beneath that methane haze, Uranus turns out to be far more dynamic than the 1986 images suggested. In 2014, observations from the Keck Observatory in Hawaii recorded a series of unusually large storms in Uranus's northern hemisphere. One storm system was so bright in infrared light that it reflected roughly 30% of all the sunlight hitting the planet at that wavelength, making it, at the time, the brightest atmospheric feature ever recorded on Uranus. It was bright enough that amateur astronomers using ordinary backyard telescopes were able to spot atmospheric detail on Uranus for the first time in history. Longer-term observations have revealed something even more interesting. Uranus's atmosphere changes with its seasons, just on an extremely slow timescale. The Hubble Space Telescope tracked the planet for roughly 2 decades, watching as it moved from equinox toward its northern summer solstice. Researchers found that atmospheric brightness and storm activity were highest around the 2007 equinox, when sunlight fell most evenly across the planet. As Uranus has moved toward its 2030 summer solstice, haze has been steadily building up over the North Pole, which has grown noticeably brighter in images, while the South Pole has darkened as it sinks into decades of winter night. This tells scientists that sunlight, even the comparatively weak sunlight reaching Uranus, still drives real atmospheric circulation, with gases sinking near the poles and rising elsewhere. Because of the planet's extreme tilt, Uranus is the only planet in the solar system where the poles actually receive more total solar energy over a Uranian year than the equator does. That makes its seasonal extremes unlike anything else we know in the solar system. There may be a second heat source as well. Researchers have proposed that interaction with the solar wind heats the upper atmosphere, a process not clearly confirmed on any other planet. Interestingly, as solar wind pressure has gradually weakened since around 1990, the temperature of Uranus's upper atmosphere appears to have dropped along with it, a possible link between space weather and a planet's atmosphere that scientists are still working to understand. Still, compared to Jupiter, Saturn, and Neptune, Uranus's atmosphere remains relatively quiet. Those other giant planets retain a lot of internal heat left over from their formation, and that heat drives powerful storms and strong atmospheric circulation. Uranus does not seem to have much internal heat left at all, which is itself one of the central puzzles of this planet. Two studies published recently found that Uranus does emit a small amount of internal heat, just barely more than it receives from the Sun, about 15% more. Neptune, by comparison, emits more than double the energy it receives. So Uranus has not completely lost its internal heat, but it has lost almost all of it, far more than its very similar neighbor. Why would two ice giants of comparable size end up so different? One leading explanation connects this directly back to Uranus's tilt. Detailed computer simulations, tested across more than 50 possible scenarios, suggest that roughly 3 to 4 billion years ago, a young Uranus was struck by a massive object, somewhere between 2 and 3 times the mass of Earth, likely a rocky, icy protoplanet. The impact was violent enough that, within a matter of hours, it could have knocked the entire planet onto its side, producing the extreme tilt we see today. According to these simulations, most of the impacting body's material did not escape. It merged into Uranus, settling as a hot, dense, energy-rich layer deep inside the planet's icy interior. That buried layer may act almost like an insulating blanket, trapping heat inside rather than letting it escape to the surface. If that is correct, it would help explain both Uranus's extremely low temperatures and its unusually offset, oddly tilted magnetic field, since that field is generated somewhere within this disrupted, asymmetric interior rather than around a clean, centered core. Uranus's moons and rings add another layer to the story. The planet has 13 known rings, all dark and narrow, very different from Saturn's bright, broad system. Among its moons, 5 stand out as the major ones: Titania and Oberon, the 2 largest, Umbriel and Ariel, and Miranda, the smallest of the 5, but in some ways the strangest, with towering canyon walls and a surface that looks like it was partly shattered and reassembled. All of Uranus's larger moons are named after characters from the works of Shakespeare and Alexander Pope, a tradition that sets the Uranian system apart from every other planet's collection of moons. Miranda deserves special attention. Despite being the smallest of the 5 major moons, it has one of the most extreme landscapes in the entire solar system, including Verona Rupes, a cliff face that may be more than 10 kilometers high, among the tallest known cliffs on any body we have observed. Some scientists think Miranda may have been shattered by an ancient impact and then reassembled by its own gravity, which would explain its strange, patchwork appearance. Today, Uranus is known to have 28 confirmed moons in total, with new small moons still occasionally being found in archived data decades after they were first photographed. The James Webb Space Telescope has added its own chapter to this story. In 2023, JWST captured Uranus's faint rings glowing clearly in infrared light, along with a previously hard-to-see inner ring, and it also detected the planet's polar cap, the same bright haze region tracked by Hubble, standing out sharply against the darker surrounding atmosphere. JWST has also observed Uranus's aurorae, the glowing regions created where charged particles interact with the planet's strange magnetic field, giving researchers another tool for understanding just how unusual that field really is. All of this, the extreme tilt, the unusual interior, the offset magnetic field, the surprisingly active but cold atmosphere, adds up to a planet that does not fit neatly into our models of how planets form and evolve. And Uranus matters well beyond our own solar system. Surveys of planets around other stars have found that Uranus and Neptune-sized worlds, broadly called ice giants or subneptunes, may be one of the most common types of planet in the galaxy. Understanding our own ice giant up close could tell us a great deal about countless worlds we will likely never visit directly. That is part of why returning to Uranus has become a serious priority. The 2023 Planetary Science Decadal Survey, which guides NASA's long-term mission planning, named a Uranus orbiter and atmospheric probe as its top priority for a new large-scale planetary mission. A dedicated spacecraft could measure the planet's interior structure, sample its atmosphere directly with a probe, and study its moons and rings up close for the first time since 1986. There is also a practical reason for urgency. Launch windows that allow a spacecraft to use Jupiter's gravity for a boost toward Uranus only come around periodically, and one such favorable window opens in the early 2030s. Missing it would likely push a Uranus mission back by years, possibly by another decade or more. If a Uranus orbiter and probe mission launches on schedule, current proposals suggest it could take well over a decade to actually reach the planet, meaning the scientists planning it today may not see its first real results until the 2040s. So we find ourselves at an unusual moment. A planet largely defined by a few hours of data collected nearly 40 years ago is now, thanks to patient remote observation, revealing storms, shifting seasons, a strange magnetic field, and clues to a violent ancient collision. Whether a new spacecraft reaches Uranus in time to test these ideas up close remains an open question. But for the first time in decades, it is a realistic one. Uranus may be cold, distant, and easy to overlook, but it is also one of the most genuinely strange worlds in our solar system, and in many ways, one of the most scientifically important.